Thanks for the introduction and thanks for having me. So in this talk, I'm going to focusing on the turbulence in outer protoplanetary disks. And my collaborators, Eleonora is my summer student last year. She's we just had submitted a paper last month, and she will be doing her Part 3 in Cambridge. She is a very good student. Henry Lecter is my supervisor here at DAMPT, and also Ming Kai-Shen and Gordon are my collaborators. We have been collaborating or collaborated on various projects. So a little background introduction about the protoplanetary disks, about the disk ionization fractions. So the ionization fractions in the disk is can be divided into two parts, the thermal and non-thermal ionization. The thermal ionization is primarily set by the disk temperature, which is primarily passively determined by the protostar. So from the stellar X-ray, far UV, and EUV radiation. However, the radiation from the star is not too hot to fully ionize the gas in the entire disk. It is only in the very inner region, less than 0.1 AU here. The temperature can reach about 1000 Kelvin, and the gases, the hydrogen molecules mainly are fully ionized there, and we're in the ideal MHD regime. But we go further out in the disk, larger than 0.1 AU. The stellar radiation is weak to fully ionize the gas, and we need to consider non-ideal MHD effects. We have also non-thermal ionization from the cosmic rays, etc., but this non-thermal ionization is also weak. So in the outer region of the disk, the gas is not fully ionized within non-ideal MHD, and the classic magnetorotational instability, which is considered to drive the disk equation, is dampened or suppressed in the protoplanetary disks. Okay, so the non-ideal MHD effects manifest in the induction equation. On the right-hand side, the first term is the inductive term, which presents in the ideal MHD, and the second term corresponds to the non-ideal MHD terms. The ohmic resistivity, the Hall effect, and amplifier diffusion. So at the same ionization fraction level, the amplifier diffusion dominates at very low densities and high magnetic field strengths, and the ohmic resistivity dominates at the high densities and low or weak B field strengths, and the Hall effect is in between. So in a disk, the ohmic resistivity is in the midplane of the disk and also in the inner region of the disk. The amplifier diffusion dominates at the outer regions of the disk and the surface of the disk, and the Hall effect dominates in between. Okay, so as I just mentioned, the non-ideal MHD effects could suppress or dampen the magnetorotational instability in the disk. So we need to find a way to transport angular momentum and drive disk accretion. And people find that it is the magnetized disk wings which dominates the accretion in the protoplanetary disks. But this is a bit problematic because it leaves the main disk body laminar. But we do need some turbulence in the disk to confront observations. And in the recent years, hydrodynamic instabilities are invoked to drive some turbulence in the disk. And even though the magnetorotational instability is dampened, there could be still some very weak MI turbulence in the disk. So in this talk, I will focus on two instabilities, the magnetorotational instability and also a promising hydrodynamic instability called the vertical shear instability in the protoplanetary disks. Okay, so for the first part is about the MI turbulence. we did some global non-ideal 3D non-ideal MHD simulations via the Athena++ code. It's 3D, but we just simulated a wedge, so the 5 domains from 0 to pi/4. We use the static mesh refinement, so we have more mesh grids in the midplane and less mesh grids in the poles. There are 2 parameters in the simulations, which the first one is the ambipolar diffusion Alsace number, which parameterizes the strength of ambipolar diffusion. And the other one is disk magnetization, parameterized by the plasma beta, which is defined by the gas pressure over the magnetic pressure. I'm going to show a movie for our Fiducial simulation. So on the left panel is the radial velocity. The middle panel is the B theta, the meridional magnetic field, which you can consider it as just a vertical magnetic field at the midplane, and also the azimuthal magnetic field B phi. I'm going to play it for another time. So you can see the left panel, the MI turbulence gradually present, and it go towards the large radii. The black curves are the magnetic field lines. So if you look at the atmosphere, the gas are coupled with the magnetic fields, which means the magnetized wings are launching. In the main disk body, looking at the middle panel, you can see some magnetic flux. They are concentrated at different radii, which is very interesting finding, and I will describe this magnetic flux concentration in detail. Okay, so about the magnetic flux concentration, it is initially found in a few years ago in ideal MHD simulations in a local sharing box for the MI. If you look at the left panel here, is the colors are the vertical magnetic field strengths. The x-axis is the time, the evolutionary time, and the y-axis is the radial direction, the radial locations. So you can see that there are 2 concentrated flux sheets formed in this local simulation. And if you look at the density, you can see that the densities are quite low at the locations of flux concentration. So this is in local sharing box simulations. Then people did some global simulations in 2D and 3D, even though their resolution is a bit low, but they find that the same conclusion. So the black curves and the white curves are the magnetic field lines. And you can see these lines are concentrated at different radial locations in the disk. And also at these flux concentrated locations, the densities are quite low. So our simulation results confirmed the previous simulation and let us to look at the detailing of this flux concentration phenomena. So I'm showing the space-time diagram of the vertical magnetic field strengths. So the colors are the BZ strengths. The y-axis is the time, and the x-axis is the radial location in the disk. Different models present different ambipolar diffusion strengths. So the left 3 ones, they have strong ambipolar diffusion strengths, and the right one, the ambipolar diffusion is very weak. So look at this left 3 panels. You can find that the concentrated flux sheets, some of them are quite static. They do not move over time. such as the left one and the third column. And some of them, they are quite dynamic. They can emerge or split over time. If we look at the right one, it's a bit different because the amplitude diffusion is weak. So we are more in the ideal MHD regime. So the magnetorotational turbulence, instability turbulence will disrupt the flux concentration in this model. Okay, so that's for the B field strands. So that leads to the surface density variations. I'm going to show a movie. The y-axis is the surface density and x-axis is the radial location. So we can see that as time evolves, the surface density shows some bumps at different radial locations corresponds to the locations of flux concentration. And the density variations involve over time. Their typical variations span from 15% to 50%, and the characteristic width is about 1 to 5 gas scale height. So this is important because it might explain some observations by ALMA D-sharp program, which stands for the disk substructures at high angular resolution project. So if you look at the right panel, the image here, some of them showing some rings and gaps in the equation disks. So this plots are the continuum decimation, and those rings and gaps might be explained by the flux concentration, because as we have seen in my previous slide, the surface density shows some bumps at different locations. So these bumps might correspond to the ring-like structure in these observations, but also notice that there could be other explanations involving a planet, the planet disk interaction, where the planet can carve a gap in the disk. Okay, so that's about flux concentration. Some other properties in our simulation is about the azimuthal features, because the simulation is 3D. So we might want to see some vortices in the azimuthal plane, the R5 plane, but it's probably due to our simulation, the phi domain is a bit small. It's because the presence of magnetic field, we don't see any azimuthal vortices in our simulations. The angular momentum transport in the disk is dominated by MHD disk wings, although the weak MI turbulence can also make contributions. Some statistics about the turbulence levels and the stress levels in the disk. So the turbulence velocity is about 0.01 to 0.1 of the local sound speed, and the stress, the dimensionless alpha parameter is about 10 to the minus 4 to 10 to the minus 3. So that's the simulation for weak MI turbulence. But if we did another simulation with very short cooling time in the disk, which means it is the condition for the vertical shear instability, which will be the second part of this talk. So I will just address here that once we have very fast cooling, we find that when in the models where the MI turbulence is very weak, the VSI can dominate or coexist with the MI in the disk. And also the flux concentration phenomenon is very robust. It presents even though the vertical shear instability sets in. Okay, so that's the first part of my talk. In the second part, I will introduce vertical shear instability, which is a very promising instability in the protoplanetary disks. So just for your information, it's not just VSI, there are other hydrodynamic instabilities. such as convective instability, the subcritical baroclonic instability, and also zombie vortex instability, and etc. This hydro instabilities, the onset of these instabilities depends on the thermodynamic conditions and disk stratifications. So for example, the VSI requires very fast cooling in the disk, and it requires some vertical stratification of angular velocity in the disk. So the plot I'm showing here is the active zone for different hydrodynamic instabilities. And we can see that they are greens for the VSI, and it pretty much spans from about 0.5 AU to over 100 AU. So it's really extends towards a large part of the disk. About the VSI instability criteria, there are two conditions shall be satisfied for this instability. The first one, by its name, stresses the vertical shear gradient in the disk. So this term actually manifests in the second inequality of the Sobol-Coiland criteria. The omega squared dz term here corresponds to the vertical shear gradient. And another condition is the fast cooling rate to remove the vertical stabilizing buoyancy effect. And this corresponds to the first term in this inequality. The nz squared is the buoyancy frequency in the z direction. Okay, so the vertical shear stability is initially discovered in the context of differentially rotating stars back to 1960s by Goldreich. It is until very recently it's being applied to protoplanetary disks by Nelson. He did some hydrodynamic simulations on the VSI with simplified disk model, and he found that VSI can present and sustain in the disk. Then gradually people add more and more physics to it, such as the radiative transfer. And also people did some 3D simulations, hydrodynamic simulations, and they find in the R5 plane, in the azimuth plane, there are some small vortices formed in those simulations. Also, the protoplanetary disks are the birthplace of planets, so there are dust particles embedded in the disk. And once we incorporate dust in the simulations, we find that the vertical motions of the VSI turbulence could stir up or mix these dust particles. And once we have the back reaction of the dust to the gas, there will be some instability called stream instability, and this will lead the dust concentrations in those stripes in the disk. Okay, so those simulations I showed are hydrodynamic simulations, but in a realistic protoplanetary disks, the disk is embedded by a large scale magnetic field. So we want to know the VSI behavior in the ideal MHD regime. So Herrick did a local incompressible sharing sheet linear analysis in the ideal MHD model. And so the plot I'm showing here, the x-axis is the B field strength, the magnetic field strength, and the y-axis the case wave number. So it's radial wave number over the vertical wave number. The yellow region here corresponds to the magnetorotational instability, and the upper left corner is corresponding to the VSI. So he found that the maximum MI growth is much greater than the maximum VSI growth rate. And the MI has very long radial wavelengths, while the VSI has very long vertical wavelengths. The MI favors relatively strong magnetic fields, but the VSI favors very weak magnetic field, which means the VSI is suppressed in the ideal MHD regime. Okay, so as I mentioned earlier, the non-ideal effects is very important in protoplanetary disks. So people also studied the effect of non-ideal MHD on the VSI. So my work and also Henrik's work both showed that when we have a big resistivity, so again, the real region is for the magnetorotational instability, and upper left corner is for the VSI. When the resistivity is weak, the VSI is weak, MI is strong. But when we gradually add more resistivity to the disk, the MI is suppressed, and we see the VSI is revived. So which is a good thing, because that means the VSI is quite robust in non-ideal MH-dominated disks. So that's purely linear theory. I did some numerical simulations on the VSI with non-ideal MHD effects with ambipolar diffusion with running by, and I'm going to show a movie. So the middle panel, the left panel is the gas density middle panel. We see it as the meridianal velocity or vertical velocity at midplane, and the right panel is the azimuthal magnetic field. So look at the middle panel, we can see that those large-scale vertical oscillations, they are the characteristic of the VSI in its nonlinear evolutionary regime. Okay. So in the next topic, I will introduce how the VSI saturates in the protoplanetary disk. So all the previous simulations, including my simulations, showing that in the nonlinear regime, the VSI saturates by those large-scale vertical coherent vertical oscillations in the disk. But the problem is that when you have the energy put in by the vertical shear, you need to have some energy put out. And this is usually done by the viscosity in the disk. But the problem here is that the coherent vertical motions, their scales are way too large. But the viscosity need to small scale patterns to dissipate them away. So, so the problem is that how the VSI saturates, how this energy can be dissipated away in the disk. So Henrik and I proposed a way by a parametric instability. So to understand the parametric instability, the first thing we need to know is that the VSI is an overstability. It destabilizes inertial waves, which is found by Adrian and Letta back about like 7 years ago. And so, so the corrugation modes, so these vertical motions, they are the inertial wave corrugation modes. Okay. So another thing for the parametric instability is that what is a parametric instability? It is the wave-wave interaction or the resonance interaction of different waves. This is like a singer can shatter a glass by using her voice. So in that case, we have two-wave coupling. The voice of the singer, the frequency is the forcing frequency, and once this frequency matches the natural frequency of the glass, the resonance happens, and this is for two-wave coupling. In our study, the parametric instability is for three-wave coupling. So you have the sum up of the frequencies of the first two waves equals to the third wave. Or more strictly speaking, you can have both plus or minus sign in front of these omegas. So I will not go through the maths here, but the overview, the basic idea is that the VSI is inertial wave corrugation mode, and this inertial wave can go in resonance with another 2 secondary inertial waves in the disk. And these 3 waves go into resonance. So the secondary waves can grow exponentially in the disk by extracting energy from the VSI wave. And so the secondary waves can grow. Instead of showing the detailed math, I'm showing here a numerical simulation, which is a 2D simulation, local incompressible showing sheet. And the code we're using is the Snoopy, which is the spectral code. So the initial condition is purely VSI wave. The X and S domain, there has 1 wavelength of VSI wave. Resolution is about 64 cells per wavelength in both directions. And for simplicity, we just take Kx over Kz equals 1 in the simulation. And the equations we are solving is the equation of motion and the incompressibility. So here is the simulation results. The colors are the azimuthal velocities. We can see that at t equals 0, that's our initial condition, so that's purely VSI wave. But as time is involved, we can see that this VSI wave, they are disrupted by the secondary waves. And the secondary waves, they have much narrower wavelengths than the primary VSI wave, as we can see in the right bottom panels. And gradually the secondary waves takes over and dominate in the simulation. Okay, so to better compare the simulation results with the linear theory we derived, we'll look at the Fourier amplitudes of selected wave modes. So the black curves here is the primary VSI wave, and the blue curve and the red curve, they are the wave modes, the initial wave modes predicted to grow in the linear theory. So we plot their Fourier amplitudes using simulation data. And we can see indeed this linear theory predicted modes, they go exponentially in the simulation. And the secondary waves, they have narrower wavelengths. So which means we require high resolution to resolve these secondary waves in global simulations. And also, so the Fourier amplitudes of these 3 modes showing that the VSI wave is gradually decreasing, and the amplitudes of the secondary waves are increasing. So which means the secondary wave take the energy from the primary VSI wave. So the simulation I just showed is a simplified local simulation, local sharing box simulation. There's no disk stratification. So one question to ask is, can we see this parametric instability in global simulations? There's some work done by Leeds and Numerical. They're studying the resolution dependence of the VSI in the hydrodynamic limit, and they reach very, very high resolution, about 200 cells per gas scale height in the simulation. So the left panel is a plot for the velocity vectors in the simulation. And we can see that there are some very small vortices in the RZ plane. It's the meridional plane rather than the azimuthal plane. So on the right-hand side, I'm showing a velocity vector of the inertial wave. And compare these 2 plots, we can see that those vortices seen in the Leeds simulation could be evidence of the parametric instability, because the it seems like the is consistent with the our linear theory predicts. So that might be the evidence of the secondary inertial waves excited by the parametric instability in the simulation. Okay, so that's pretty much all I want to talk about. Just to quickly sum up, we studied the saturation of the vertical shear instability via parametric instability. The parametric instability requires very fine resolution to capture, and it requires about 300 cells per Pascal height in the global simulations. The BSI is likely far more disordered and incoherent than the current global simulations suggest. We also carried out global simulations, 3D simulations with ample diffusion applicable to outer protoplanetary disks. And we find the magnetic flux concentration is quite generic and robust in those ample diffusion dominated disks. And the magnetic flux concentration results in substantial variation, which might explain the observations of the rings and gaps by the ALMA observations. And also we study the angular momentum transport in those disks, and also the turbulent levels and the alpha parameter. So I guess I will stop here and take questions.